First thank a lot of contributors. Engineering like this happens only when a lot of really good minds get together and come up with ideas, and this is a partial list of some of the great minds that have worked in this area. I also show you one picture. If there's anything you want to carry out of this talk, you should carry that we can, using packaging technologies, do heterogeneous integration in all three dimensions, and it gives you tremendous flexibility to build products by intelligent mix and match. The talk is broken, as I said, in two parts. What we will do is we will start by describing the package as a compact, heterogeneous integration platform. I will speak primarily about on-package interconnects and how it enables high bandwidth signaling. I will briefly speak about power delivery and the complexities of power delivery, even more briefly about the complexities of thermal management. And then I'll hand over the talk to Dr. Sandeep Sane, who will be the second presenter, and he will talk to you about assembly processes, the importance of materials and design. In the second half of our presentation, we will describe product implementations that use these advanced packaging technologies. So you will see how the thought I describe here translates into products that offer performance. The talk outline is this. I will speak about the package as a compact heterogeneous integration platform. I will describe how we think about package interconnects and how we enable high bandwidth signaling using packaging interconnects, and then power delivery, thermal management, and then we will transition to the assembly processes, materials and design tools, and come back for a quick summary. If you look at the package and ask the question, why the tremendous interest in heterogeneous integration? And if you look at the history of the evolution of packaging, you will realize that there has always been interest in the package as a heterogeneous integration platform. In recent years, people have realized that you can use the package to do many things. You can use it to mix and match diverse IP, and you don't have to integrate all of it if you can't for whatever reason. You can optimize IP on different processes and integrate it on the package. You can use the package as a means to escape reticle limits. You no longer have to be restricted to the size of a reticle on a wafer. You can get more silicon on a package, and for heterogeneous technologies, it is a great platform. The other is that over time, there has been a need, and there will continue to be a need, if I understand architecture, for proximate memory, which has high bandwidth and low power to enable performance. And then the basic reasons why the package has always been of interest as a heterogeneous integration platform. First is yield resiliency. The new processes, if you want to make chips smaller to get better yields, you can always integrate on package. And by being able to mix and match on the package, you can make time to market, you can make products available to the market faster. All of these make the package an extremely attractive platform for you to integrate different elements and complement the advantages of homogeneous integration that we have gone used to over the years. Okay. So let me illustrate what I mean by this by showing you some really interesting use cases. The first use case was presented at the 2020 ERI Summit by Sergei Shumarayev. In this, he showed that you could take an FPGA and you could integrate different things on that FPGA. You could integrate custom ASICs. You could integrate, interestingly, optical chips, and you've seen announcements of this nature in the last few years. They allow you to do EO or OE conversions very, very close to the FPGA, and the FPGA is connected to the O-tile, for instance, using a high bandwidth, low power interface like AIB. And then an announcement you saw just a few days ago at Intel's Architecture Day, the Ponte Vecchio, which we will get into more detail later. The one thing you can carry out of this is the level of integration that is enabled by Ponte Vecchio or this class of processors is simply unprecedented. So this sort of gives you the perspective, and now let's dive a little deeper into what does it mean when you say you have to develop a package as a compact heterogeneous integration platforms you need to focus on. Before I get started, let me point out that this is still a limited set of factors, and there are lots of publications out there that describe in their entirety all the factors that are important. What I will focus on are the ones that are highlighted by the red boxes. I will spend the most amount of time on ensuring that I communicate how to deliver power efficient, high bandwidth I/O links on package. I'll also speak, but not I get into detail outside of the example in the previous slide, that we have to make sure the package is also capable of delivering a diversity of off-package I/O protocols. Doing signaling right on package is a very important aspect of successful package integration. As you start bringing diverse IP on the package, you will have to worry about how to cool it. And I will briefly describe what it takes to cool it. I will also very briefly describe what it takes to deliver power to all the different functionality you integrate on a package. And then I'll hand it over to Sandeep to talk about how we do cost-effective, high precision, and quick turn assembly for the success of the package moving forward as a heterogeneous integration platform. We have to make sure that we focus on all aspects of design, manufacturing, materials and process, and reliability. And Sandeep will give you a brief overview of this. The topics we don't cover for time are reliability and functionality, but they are covered in a more broader heterogeneous integration roadmap that Intel is a part of. Okay. So now let me dive a level deeper. Let me talk to power efficient, high bandwidth on package links and what it takes to deliver these kind of protocols. If you take a step away from what a package does, essentially a package takes connections on the die. For purposes of this discussion, these are bumps on the die. These bumps land on pads on the package, and then wires route out laterally from the edge of the die. Now these wires route out laterally not in one layer, but in multiple layers. So if you want to extract some physical metrics, you can extract two metrics that are of importance. One is the wiring density. How many wires can we connect between two die on a package? Or how many wires can we deliver that go outside the package and connect in the system? If you want more interconnectivity, then you have to focus on increasing the wiring density. What that means is you can reduce the width of the wire, you can reduce the space between the wire, and you could reduce the size of the pad on which the bump lands or the vias land in underlying layers. Ideally, if you had a system where you have 0 pads, you get the best wiring density. Similarly, if you want to get more and more connectivity out of a die to the package, you should focus on reducing the density of the bumps. Okay. So let me offer an Intel-centric view of, but before I do that, let me just quickly go back to the previous slide and talk to you about two dimensions. The two dimensions I spoke about are wiring density, lateral, number of wires per millimeter of the die edge on a single layer. Okay. And the other one is the bump density, which is an areal metric, the number of bumps per unit area. Okay. These two metrics, and for some reason, even though these are physical metrics, they are called I/O as well, so I will interchangeably refer to the two. Now let me offer you the current state of advanced packaging. Since I am from Intel, I'll offer you an Intel perspective, but you will hear different perspectives from different people, and you will notice that there is a common theme. The common theme is simple. You can get interconnect density in a planar fashion using planar MCPs, oftentimes referred to as advanced packaging using 2.5D if you put stacks of memory next to the compute. And one way of doing it is to use what we call EMIB, or the Embedded Multi-Die Interconnect Bridge. The vertical interconnects, something that has been of tremendous interest for many, many years now. Intel's instantiation of the 3D integration, if you will, or the Z-plane integration, is through Foveros. In this instance, I show you where active die are connected to active die. And now that you can connect in a lateral manner and a vertical manner, why not combine the two? So you combine the concepts of EMIB and Foveros and do both lateral and vertical connectivity. The images in the bottom show you that these are ideas that have now proliferated into manufacturing and are available for designers to make real use of to convert into products of great interest, which we will talk to later in this presentation. So let's talk about planar interconnects. Okay, I will avoid use of phrases like 2D, 2.5D, or 2.5D and all that kind of stuff. Just very, very simply look at the question of how many wires can you escape from the edge of the die on a package. Okay, for this we take a metric like the half line pitch, okay, which essentially is nothing more than number of wires between two points such that you can repeat beyond that per unit length. Okay. If you look at this graph, it plots the number of wires you get per millimeter per layer as a function of different technologies. At the bottom right, you will see the traditional organic packages. These are the workhorse of the industry. These have been around for a very long time, for the last at least 25 years, and essentially give you wiring densities somewhere in the 30 to 50 IO per millimeter or wires per millimeter of die edge per layer. Okay. And these are pretty good when you form interconnects which are essentially used for high bandwidth interconnect and for different components on the die that don't need the density. Okay. If you want more wires, you learn to print your wires better, which forms the second class of interconnects, which are the high density organic interconnects. These are with organic dielectrics. They have a certain class of advantages, and there is interest in these kind of technologies. The third broad class of technologies are the technologies that use silicon back-end wiring. Now we are approaching the density problem from the other end, as in instead of shrinking wires, we are actually taking the silicon back-end wires and making them thicker and thicker. Even then, when you start at 2 micron wires and 2 micron lines, you get 500, you get 250 wires per millimeter. You can get down to 500 with 1 micron. Half a micron, you get to 1000. You will notice that with silicon, where you land the vias without pads, you get rid of the pad effect and you use silicon backend technologies. If you look at this, you now have a series of technologies which give you a very wide diversity of interconnect density. The focus among the packaging community is to make sure while we deliver this interconnect density increase, we also deliver power efficient connections for increased bandwidth. So now let me switch over to the third or the second class, the 3D interconnects, where I focus on increasing the bumps per millimeter square. Okay. The workhorse of the industry today for 3D stacks is to use solder-based interconnects. Solder-based interconnects can give you tremendous connectivity, and somewhere in the range of about 25 and south of 25, though the exact boundary is not defined, you would have to transition from solder to copper-copper interconnects. And the copper-copper interconnects can shrink density quite a bit. So again, you have a very broad portfolio. When I have given this talk previously a few years ago, I used to say that somewhere in the 20-25 micron range, we will transition from solder to copper. But technologists, as always, prove you wrong. There is a paper here that shows you can shrink pitch below 20 microns. The transition will not be dominated only by the type of interconnect, but it will also be dominated by other factors, including alignment, reliability, etc., flatness, etc. So somewhere there will be a transition, and that transition is already in force today. We can transition from solder to copper, and there are very good demonstrations, which I think a speaker in this talk, in this session, will also describe. The third type is how do you transition from 2D, how do you combine 2D and 3D? You can do it what I describe as co-IMIP, where you take multiple top die tiles on a base tile. You take multiple stacks of these tiles and you connect them to each other using IMIP. You connect them to peripheral components. You connect them to peripheral memory. You notice that now you have in your hands very, very powerful methods by which you can integrate a lot of stuff on a package. Okay. Why do this? Why do all of this, and how do you define a packaging roadmap? So in this one slide, I make the case for three things. One is, even though we are giving increased connectivity, there is a growing demand and a continuous demand for increased network and bandwidth density and speed. The graph on the bottom right is pretty educational. It says that even though we increase bandwidth, we also are seeing that as peak flops grow, the bandwidth per flop actually trends to go down, and there is a need to pull this curve up. So Packaging engineers, I suspect, will be in business for a long time because we will have to continue to offer methods by which bandwidth can be provided on a package. I will describe one class of on-package bandwidth scaling where the die are very close together, and we are focusing on this class of bandwidth scaling for a very simple reason. Looking at this graph, you come to the conclusion pretty simply that if you provide more and more wires, you can essentially develop interconnect which we describe as wide and slow. You get higher bandwidth with the use of simple circuits, so you have a chance to get to lower power, and we focus on designing interconnects so that the signals are not lossy. The reach of these are limited, but they have a very, very viable use case as you will see in later parts of this and the next talk, where we describe architectures that make use of this. So I made a case that you must connect elements on a package and they must have high bandwidth and low power. This is the basis of forming a roadmap. I here describe to you a roadmap that has been created through a consortia of people in IEEE, the American Society of Mechanical Engineers, SEMI, and industry and academic participants. We describe a generation as one where you double the raw bandwidth density, as in our focus is on providing the physical interconnect hierarchy. If you look at side-by-side or planar interconnects and look at the high density, high bandwidth interconnects available today, you can use the HBM instantiation as the first point in time where you can connect different die. Okay. Today, HBM is done at 55 micron pitch. In one particular case, when you send signals at 2 gigabits per second, you can accomplish this using a I/O per millimeter square of 331 and an I/O per millimeter of 500. By the way, this is not I/O per millimeter per layer, but it is the total I/O per millimeter. If you double it, I show one example, and I should point out that this is a non-unique table, as in you can accomplish bandwidth doubling by changing different parameters. So this is one good way of doing things. Okay. If we stick to solder-based interconnects, where, as I said, the pitches are limited to north of about 20 microns, so if we pick 30 microns, you can accomplish bandwidth doubling generation over generation with signaling speeds at 8 gigabits per second, pretty reasonable, and at a pitch of 30 microns. Okay. You will pay some penalty in terms of shoreline area and die area, but you can accomplish doubling. If you say HBM is the first generation, you can reasonably assume that columns 1 and 2 or gens 1 and 2 are what is real today, which means we have a lot of runway in developing this bandwidth. Now suppose we use more aggressive bump pitch scaling techniques and we shrink the pitch more aggressively. You can still accomplish the same thing with much, much higher areal density of bumps, similar speeds, so you can get die area and die edge advantages. The point you should take away from this is there is a lot of runway for us to do planar scaling of bandwidth on a package, and packaging technologies realistically can hit generation 5 and more, so there's a lot of runway. A question I often get asked is what is the duration between generations, and I always answer by saying that it is about 2 to 3 years or maybe more depending on other factors. But you can now start doing the math, and I have seen instantiations where very, very good engineers have demonstrated what it takes to go past 5 generations, which means there is more runway here than I show. And you can read about this in the heterogeneous integration roadmap. If you look at 3D scaling now, in 3D, our starting point is what used to be the starting point of the wide I/O interconnect at 40 micron pitch. Here also I show a way by which you can hit tremendous bandwidth densities. You can double generation over generation, similar duration between generations, and you can end up getting bandwidth doubling for at least 5. And engineers are pretty skilled, so you can easily infer that you can go past 5 generations. Again, the same point, packaging has a long way to go. So that was interconnects, the infrastructure provided to offer bandwidth scaling. Now let me switch to describing power delivery. The role of packaging is, while it brings different IP together and creates a compact platform, it is also to deliver power to each element on that platform. and as needed through separate power delivery networks that coexist. This increases complexity because you're bringing things together. By itself, this is a pretty deep field. I'm going to, for time, be somewhat superficial in the way I describe it by focusing on one element or one style of instantiation. But a lot more can be discussed in this area. So the way to think about this in my mind is, for purposes of this talk, how do we bring different IP on a package, connect them to deliver power to all those IPs, make the power delivery path as efficient or as less parasitic as possible, so power is delivered as needed, as fast as possible, and with the right quality so that we can deliver performance. So a brief look at history is always useful to see how things work. Historically, most people in the 1980s up to the early 2000s focused primarily on frequency scaling. So the goal was to enable faster and essentially leaky transistors, and frequency was the name of the game, right? So you would scale the threshold voltage, you would scale the device dimensions, and you lived with increased leakage and active power. In the mid-2000s, there was a transition away from single-core architectures to multi-core architectures. This was an effort to look at other performance characteristics and not just frequency scaling. More cores offer you performance, and they allow a transition away from focus on single-core optimization to multi-core optimization. Part of this is we wanted for power efficiency to get fine-grained power control. So we had to offer different voltage rails that could be independently controlled. And so you see here now, with time, and this is a representative graph, with time the number of power rails on a product as the number of cores increased also increased steadily. And depending on functionality, in servers you have more cores, so you have more power rails. As I mentioned before, we are going to talk about one particular means of delivering power, which is Fiver, the fully integrated voltage regulator. Intel introduced it on its 4th generation of the Core microprocessors, and the idea was that you on die or on package are able to step down 1.8 volts to an array of output voltages. By having independent power rails, you have control, and by having control, you can control the power dissipation, as in get more and more power efficient devices. Okay. This is an example of how Fiver was instantiated. This is a physical example of how power was instantiated. I think one of the big things we managed to do in this time frame was to utilize existing features on a package, the plated through holes or PTHs, and create what we call ACIs or air core inductors. Okay. This instantiation shows you how the VRs are implemented on die and how the ACI are used to deliver power and to control the delivery of power. Okay. In the first generation of the Fiver that Intel introduced, we achieved an efficiency of 90%. This was at a full Vout of 1.08 volts. And the first generation of the Fiver ACI, the air core inductors, had a high quality factor. Okay. At that time, we had a large XY footprint and we had a 700 micron thick core. We achieved 90+% efficiency at that time frame, which is pretty good for power delivery, and considering the fact that we were delivering power to multiple voltage rails using the Fiver. Okay. In time, as the process has scaled, the core area shrinks, which means we have to shrink the footprint of the air core inductors in the X and Y. With the push to thin and light devices, we went to thinner and thinner cores. Here I show one example where we went from 400 micron, 700 to 400, 400 to 200, 200 to 100 microns. Essentially what we are doing is we are shrinking the volumetrics available for the inductors. And as a result of this, we end up hurting the air core inductor performance. Clearly, there is a need to do something else. The something else is the introduction of magnetic inductor arrays. Magnetic inductor arrays have better performance, and by focusing on material optimization and form factor optimization, we have an opportunity to improve performance. For instance, the 10th generation Intel Core microprocessors used a number of magnetic inductor arrays, MIAs, for different voltage domains. Okay. The use of these inductor arrays essentially helps us recover the loss of efficiency due to ACI, area scaling. For those of you who are more of the research bent of mind, or in the advanced development stage, there is a message here. The message is that improved magnetic materials are going to help us get improved magnetic performance, and will be one vector that we will have to all focus on to continue to deliver the kind of performance we need at as low parasitics as possible. Okay. I will now transition to the last topic of my portion of this presentation, and this is just as important. As you start aggregating things together, you have to manage cooling. You have to make sure you fully understand what needs to be cooled, how it needs to be cooled, and how to make it cost effective. I started my career running a group, or at the early part of my career, I ran a group that used to do thermal management. Thermals is a very interesting and a very important topic, and fully characterizing the behavior of thermals is both technically rewarding as well as very, very useful in the packaging industry. In a single slide, I'm going to try and communicate to you that thermal management is something we ought to pay a lot of attention to. And let me try and do this. This is a busy slide, so let me walk you from the left onwards. Okay. As you take that structure I showed you before, where you have EMIB plus Foveros pulled together, you have multiple stacks sitting next to each other, you have 2 or 3 interesting problems. One interesting problem you have is that these stacks, by definition, will have different heights. It is possible to get equal heights roughly, but there will be some intrinsic difference in the heights, which means if you put a thermal interface material in between the stack and the next level that is used for cooling, you will have to manage different heights. Okay. And thermal management to a large extent boils down to first conduction. You conduct the heat from the surface of the die to the next element. It could be a heat spreader, it could be the base of a heat sink. You do it through the use of thermal interface materials. By bringing a lot of things together and by putting high conductivity materials next to the stacks, you intrinsically include thermal crosstalk, and you have to deal with thermal crosstalk. The third thing that is hidden in here is that when you stack multiple devices together, you have to pay attention to how they are designed, because now your thermal resistances add up. And to the first order, we design thinking of these as resistance models, so it's important to understand the resistances of the stack. I show you 2 technologies that we've discussed in the last few weeks publicly: the Foveros Omni, which Sandeep will offer more details on, and the Foveros Direct, which uses the copper-copper interconnect. In all of these, we pay exquisite attention to the thermal interface resistance to make sure that the designs are done right, and we collaborate with people who design our IP to make sure that we don't, by design, put hot on hot. Okay. This graph here talks about a 2D, or actually a 2 die stack which can be placed side by side, or with 2 dice which can be placed side by side or stacked on top of each other. And it shows you that if you stack them, you do inhibit the thermal capability, but by intelligent design, you can figure out ways by which you start approaching similar capability of a 2D device. Okay. How do we do this? We pay attention to a lot of things in packaging. We pay attention to the die-to-die thermal resistance, and how do we manage and understand the interface resistances. We pay a lot of attention to the thermal crosstalk between neighboring die and how they can be designed so that we have designed something which is capable of handling a high amount of power and capable of managing temperatures on different die. It's also important to note that all the die on a package don't necessarily have the same temperature or power density demands, which means if you have certain devices that have to be at a lower temperature compared to the next, you have to manage the thermal crosstalk between them. We also look at very carefully how do we design it so that the power density is under control. One of the few things Intel has done over the last few decades is get very, very good understanding of the different power densities, power density maps, and through models and calibration figure out what is the impact of these and how temperature must be managed on a surface or in a volume as opposed to at individual average levels. Okay. to reiterate what I said, we focus heavily on reducing the resistance between the thermal interfaces. In cases like Omni and Foveros Direct, we are getting into a higher level of detail in understanding interface performances. We have over the years developed best-in-class metallic thermal interface materials, and we have focused not only on the bulk conductivity of these materials, but we have focused on the interface conductivity and the interactions between the die and the integrated heat spreader, as well as the interactions between the die when they are lateral or vertical. And the last and probably the most important part, where there has to be a lot of collaboration, is in the design of what we call thermally optimized package architectures. If by design you design a part such that you don't bring high density spots close to each other or hot spots close to each other, or you manage the thermal density and level it out, you will get to much superior thermally designed parts. And co-design of the silicon and package to improve thermals is a very, very significant portion of the work we do. In this talk, hopefully I have given you a overview of all the factors that affect the design of packages and how we go about making the package a compact heterogeneous integration platform. I have spoken mainly about performance, and now I'm going to hand it over to my colleague Sandeep Sane, who will talk to you about the assembly processes, and he will talk to you about materials and design tools and bring this portion of the talk to a close.
Right. Thanks, Ravi. It's my pleasure to be here. I'm going to start where Ravi left. Ravi essentially covered most of the elements that were design-centric, going over the overall interconnect scaling, power delivery, thermals. But now it comes to is how do you make this real, right? And so I'm going to touch base on how do you assemble these things, these complex architectures? How do you make it effective, cost effective? And how can you scale to a real high volume manufacturing setup? So what I'm going to go over the next 10 minutes or so before I hand it over to question and answer is really provide a high level view of what are the assembly processes and some of the challenges and opportunities in this space. So if you look at the assembly and test development to enable this packaging, the primary focus of assembly technology development is to deliver high functionality parts that deliver to the product performance, but it is very critical that it delivers at a high yielding and high quality and reliability. So if you look at now in this plot, what are the high level overview of essentially any assembly technology is the wafer comes out of the fab, it is typically sorted, then it is diced, then you go through assembly process, and depending on the type of architecture, either you spend a lot of time doing wafer level assembly or you do a standard silicon to package assembly. Then you go through a final test, finish, and then it is shipped to the ODM partners where they assemble those parts onto motherboards and at the platform. One of the essential parts is what Intel is very much focused is to ensure that we create a high-yielding, environmentally friendly assembly and test processes. One of the key cornerstones of Intel assembly technology is to maximize the yield. There are you can think about in two broad aspects. One is when we especially get into this heterogeneous integration space, when we commit the die, the silicon to a package, it's good to have a known good die or a known good subsystems. So Intel, over a course of several years, we have spent a lot of time in developing what we call advanced sorting capabilities, right? There are very unique capabilities we have developed so that when we commit the die to a substrate, package substrate, it is known good. Also, over the years, there is a significant understanding we have developed on silicon package interactions and how we can develop that interactions and we can maximize through design, material developments, and assembly processes that interconnect formations and how do we maximize the overall yield. Right? But we don't stop there. We also work with our end customers. We have our own lines where we simulate what an end customers would see when we ship the parts to them, how they will experience when our parts arrive at their factories, what environments they will see. We try to simulate upfront so that OEMs and ODMs, when they receive our parts, they also experience a very good, healthy yields at their end. So essentially, we are very laser focused to look at from silicon fab when it comes out to all the way to the platform and system level. We look at all aspects and we develop technologies that support that. Now, when we look at some of these heterogeneous packaging technologies, I would like to walk through what are some of the big challenges that we see. And also, of course, these are challenges which allows us to, there are a lot of opportunities here, especially this requires a very interdisciplinary approach where people with various backgrounds, various mechanical materials and chemical engineers all needs to come together to really make this happen. Essential part of heterogeneous packaging is we need to deliver to a product performance. So meeting the electrical targets is an essential part, right? So getting the right materials that behave, provide the low loss performance for the high-speed signals or the power deliveries that Ravi covered is an essential part of what a package technology needs to deliver. It has to be, however, balanced with what the material sets can survive through assembly and test and reliability. So if you look at this heterogeneous packages, this is essentially a complex composite with a wide range of materials that coexist in this form factor. One has to optimize these materials so that it delivers to the product performance, but also meets the assembly and reliability requirements. Right? So one has to come up with materials such as underfill molds, fluxes that go within the assembly process that deliver to the quality and cleanability type of boundary conditions. One has to deliver the thermal interface materials which Ravi talked about so that it gives the best bulk conductivity at the lowest interface resistance. Not only that, with more and more heterogeneous integration, one has to ensure these assembly process and test processes that are developed, they can also integrate and mix and match silicon technologies from different fabs. And that has to be seamlessly integrated into these processes that have been developed. So essentially, that is a real complex co-optimization that is needed to deliver a good, stable, robust assembly process. The other aspect of assembly process is as we scale the interconnect, as we scale from a standard C4 type of pitch, which is typically has been around 100 microns, when we go down below 50, 40, or 20 microns, this interconnect scaling, maintaining yields is a very complex problem. Right? One has to manage how the silicon warpage, substrate warpage, and maintain the coplanarities throughout this system so that it can maintain a good, healthy interconnect yields. And in Intel, we have developed a fairly good, deep understanding of this over several years. And we are fairly confident that when we continue to scale this roadmap to a fine pitch, we can continue to maintain these very healthy assembly yields. The third aspect is really when we take a look at any architecture, when the design comes from a product point of view, we take a look at those architectures and we can model this upfront. So we can do these trade-offs really upfront so that we can optimize the designs such that we can make them successful in the downstream assembly and test processes. So there's a lot of effort that goes in to make these products a reality. And essentially, it means that one has to work not only from design space, but work with our equipment, materials, and products engagement with the right business units who are defining these products so that we can co-optimize this for assembly and high volume manufacturing setup. One of the most important element of packaging technology is the advanced substrates. As you may have heard, there is a substantial substrate crunch these days in the industry. So it is very essential to develop substrate capabilities which provide you very high yielding substrates. So there is a lot of engineering that goes into just managing the substrates and developing the capabilities so that we can continue to provide these substrates to meet the product requirements. Just if you look at what is expected of a current substrate, especially in this heterogeneous integration type of packaging technologies that we are now embarking upon, there are multiple aspects of it. One is just looking at the form factor, these substrate form factors, how they are increasing. If you look at 10 years back, the form factors, even in the high data-centric segments, were much smaller to compare to where we are today. They're becoming much larger and larger. So maintaining the yield at the substrate manufacturing facilities is very critical. When we look at technologies such as EMIBs, where we embed these silicon bridges into a substrate, it's very critical that it is precisely embedded. Plus, now these substrates have a demand to have a mixed pitch. There is a combination of extremely fine pitch for the die-to-die interconnects, as long with coexisting with a very loose pitch. So managing this pitch, heterogeneous pitch on a given substrate is very challenging, and also it also is a very good opportunities to improve the plating chemistries and the tools that are needed to deliver to the quality of these mixed pitch that are demanded by the products. Managing the materials. As the speeds increase, when we go from 56 gig SerDes to 112 gigs and in future even further, managing the speeds, the low loss materials for the high speed I/O, coupled with demand for smooth copper and demand for a certain barrier layers within the substrate is becoming very critical. So there's a lot of work that is going on in this space where one has to optimize how the laminations and surface finish that are allowed on these traces that are breaking out of within the substrate. Not to undermine, there are a lot of assembly processes to maintain the coplanarity of these substrates coming out of our suppliers, which drives a lot of planarization techniques, so that when they come out of the substrate suppliers and when it comes to assembly houses such as Intel's, the silicon can be placed on it, and then we can deal with the good assembly yields. Right? So really, if you look at today's substrate, it is a very complex activities that are needed. And Intel, realizing the needs for this, has now, we have a substrate line at Intel, which we develop, and we do a lot of R&D upfront on many of these vectors that I have elaborated, and working closely with our substrate suppliers so that we can bring these concepts in from research phase to a real manufacturing environment fairly quickly. So there's a lot of efforts that goes in, again, optimizing equipment and materials and how this integration at the substrate can be achieved. The next aspect, when we say co-optimization, it's a good word, but there's a lot of behind the scene that really goes on. These are the real, I would call, our tools and techniques that we have developed over years that allows us to do co-optimization. Right? These are really analytical tools that we have developed across mechanical, thermal, and electricals, coupled with significant investments in our lab setup, that we are able to not only do the simulations of some of these design trade-offs, whether it's a mechanical integrity of a package, when a silicon is put on a package, what happens? How does the package behaves during assembly or during test environment, or even in the actual use conditions? We can simulate all this upfront and make appropriate design choices and material choices so we can ensure this product is reliable or it is manufacturable. Same thing goes when we look at thermals. When we look at the silicon floor planning, we can model a lot of these upfront and understand how the products would behave, where are the hot spots, where do we need to offer specific, what type of thermal solutions we need to offer. Or even we can go upstream and say, how can we do silicon floor planning upfront so that we can get the maximum out of the product. These are the elements that we have invested substantially in our environment at Intel. And we work very closely with some of the leading academia and consortia to develop some of these unique tools and metrologies that are needed to validate some of these models upfront, so that when we design things, we can do these trade-offs before it comes to any manufacturing. At the same time, when we look at our materials, these are the materials are very essential. We have a strong development with our material suppliers. These are materials that can provide magnetic inductors, low loss materials, or high performance packaging passives, so that we can integrate this into a package and provide a predictable and performance enhancement to the end product that we are developing. Right? So it essentially takes all these co-optimization and the analytical tools and techniques that we have developed to really make a complex architectures that we are shown, especially when we embark into this heterogeneous integration, where we are taking silicon from different fabs, integrating on a technologies such as EMIB or Foveros, or a combination of EMIB and Foveros, to bring it all together so that we can manufacture in a very seamless manner at a high yielding process, and also deliver to the reliability that the products demand. So I call them really, these are the technical pillars at Intel that really work behind the scene to bring these concepts into reality. Right? Now, just to summarize what Ravi has said, and also what I went through fairly fast, but what we are saying, what we are observing, that there is a broad and growing consensus that heterogeneous integration has become a key enabler. Right? This is enabling technologies on a product that is becoming which is offering distinguishing features for the products. There are many aspects of when we design this on-package integration using these advanced packaging architectures. One has to be concerned about, or one has to make sure its power efficiency bandwidth is provided. It becomes a key enabler. One has to also look at some of the delivering clean power to optimize microprocessor performance, especially when you look at the increasing power rails and overall power levels required. There are new power delivery challenges that are emerging. But there are methodologies and there are systematic ways that Intel is in forefront of solving some of these challenges. Thermal management is also a continued problem or a challenge, I would say, but it also provides an opportunity to come up with the new materials for thermal interface materials that can alleviate these problems, along with some of the core design or optimizations that we are doing, right? And finally, when you look at the continued scaling, when you want to bring this into reality, there are multiple trade-offs and innovations that are needed that we continue to lead the industry to ensure that the assembly yields and reliability are met for this heterogeneous advanced packaging technologies. Right? With that, I would just stop here. We will take any questions. We have another talk at 4:45, I believe, where we will showcase some of the advanced packaging technologies